Two of the four types of facility layouts that we were talking about in this chapter, product and process layout, it pays to keep those separate in your mind, even though they sound so similar, product and process. You can see this very first question is hitting on that. The type of layout that is used to achieve smooth and rapid flow of large volume. Rapid, smooth flow, that all caught my attention, but it's this. Large volume of, oh wait a minute, standardized output is, right, of all of these, product and process are the hardest to keep apart in terms of terminology in our mind, but remember it is a product layout that produces large volumes of standardized product. Think of it as it's devoted to the product. Okay, now how do you design a product layout? That's what the next set of questions is about. All right, let's take a look. The Big Ol' Cookie Company needs a new assembly line designed for a new product. Right, because another name for a product layout very often is an assembly line. The line is to run 10 hours per day. Ooh, I might want to harvest that number. 10 hours per day. We know that is operating time. 10 hours a day to meet forecasted demand for 900 units per day. So this assembly line has to make 900 a day. The following table describes the tasks that are necessary to produce the new product. It is a standardized product, so to build one, you always need to do these things in this particular order, and each one of them takes this amount of time. The Big Ol' Company has hired you to, right, what's the whole point of this problem? Design the assembly line. You've been asked to choose the longest processing time first rule in decision making. If you can counter any ties, sometimes this is specified, the greatest number of following tasks rule will break them. Please answer the following 3 questions based on this information. Okay, so this is a line balancing problem, and we're probably going to have to do that big worksheet to divide up the tasks among the workstations, because that's basically how you design an assembly line. True, we are going to have to do all of that work for this particular problem, but notice that the first question, if you were like running short on time, you don't need to design the whole line in order to answer that question, because it just says calculate the cycle time of the assembly line, and we remember that cycle time is operating time divided by demand. Oh, which is actually one of the steps in the design. It's actually the first step in the design anyway, but this we can sort right here just by filling out the numbers that we found. Okay, so operating time is 10 divided by 900, which means, on my calculator, like 0.1111. Now, I need to be careful in answering this, because it's true that that number that I'm looking at on my calculator is a choice, but we have to remember that whatever the numerator is in, that's what your answer is in when you're calculating cycle time. And we've discovered that the budget of time that each person should have to do whatever is assigned to them on this assembly line is 0.0111 hours. Why? Because the 10 was in hours. Oh, okay. Now, we also remember that a principle from designing assembly lines is do not leave this step of calculating the cycle time until you have converted the cycle time into the same units as your duration data. Notice that we were given all our data about the tasks in seconds. We need a cycle time that's in seconds. Oh, okay, we need a cycle time that's in seconds. It's not hard to adjust that. If I multiply it by 60, I would get minutes, correct? And then if I multiply it by 60 again, I would get seconds. And that is actually where we arrive at. Try it. Put 10 divided by 900 in your calculator, you're looking at seconds. Say times 60, you're looking at minutes. Say times 60 again, you're looking at seconds. That's where we get answer C. Oh, all right, yes, and we would have needed that anyway, even though it specifies in seconds. We would have needed that anyway to continue with the design. So let's see if we can answer another question quickly. Given you followed Big Ol' Cookie's instructions, what is the efficiency of the line? Oh no, we have to go ahead and work this line balancing problem. We have to create a design in order to, calculating the efficiency of the design is like that last phase. You have to have already designed the assembly line. Okay, so I'm going to need some scratch paper, some room to work, because you can remember line balancing if you can remember the header station time remaining, eligible tasks, I'm just abbreviating it, that will fit, and assigned. These are column headers, so maybe I should put a nice kind of like column header border here. And I'm all ready to balance this line. Oh, I'm all ready to balance this line, except that you might recall from class, this is not a mandatory step. I would not try to do this without first sketching a precedence diagram. Oh, now wait a minute, a precedence diagram. I'm just going to create a network illustration of this information. Why? It's a lot easier to work with the network illustration than to work with this particular table of data. Okay, so I just want to draw a network representation of the work that needs to be done, and I do that by finding the one task here that doesn't have an immediate predecessor. Now, let's see, here's where I'm going to work. Why don't I grab another sheet of paper for my precedence diagram, because I just want to jot that A. Okay, this represents task A. Now I want to scan, actually see, now it's nice, it's on a small sheet of paper. I can do this. I want to scan this information to look for anybody who, oh yeah, I'm pointing at it, anybody who requires A as an immediate predecessor. B requires A as an immediate predecessor. That's how you illustrate that. When you're done with A, you can go on to B. Now, look at that. C and D require B as immediate predecessor. When you're done with B, you can, I'm just illustrating it, proceed to task C or proceed to task D. Either is allowed. Okay, E has C as an immediate predecessor. That's how we illustrate that. F has D and E. All right, so here's F, the task, and what we're saying is it has to be connected to both. They both have to be finished for that to start. And then G has F, and, oh, and then, okay, great. This is the network diagram. Now, in order to eliminate the need to keep paging back to this table of data, I'm also going to jot down the durations from the table. Let's see, C is 10, D is 20, E is, let's see, E is 10, got to get it right. F is 24 seconds long, and F is 40 seconds long. Okay. It's worth it to take the time. This is easier to work with than the table, because we begin designing assembly line at the first workstation. We have not assigned anybody to do anything. That means the first workstation has a full 40 seconds. You say, what? That's the cycle time to do whatever we happen to assign them. Eligible tasks, what might we assign them? Well, we have not basically accomplished any of this yet. There is only one task at the beginning, that's what you're looking for, that would be eligible for assignment. Now, will fit, it's 36 seconds long. There's 40 seconds left at this station. Yeah, it will fit, that's great. Okay, then it automatically gets the assignment. There, we have made our first assignment, which is kind of a no-brainer. I'm going to lightly mark it off the list. Yeah, duh, that one very first task would be done at the first workstation. Now, that means 40 minus this 36, there's 4 seconds left at this station. Now, at the point that we've gotten A done, B becomes eligible. The problem is that B is 20 seconds long and there's only 4 seconds left at this station, so B won't fit, which means this is just empty here, which means that we are stuck, at least stuck at this workstation. There's nothing more here we can squeeze into that budget of time, so we just shut it down and start a fresh workstation. Start a fresh workstation. Let's see, that means we have 40 seconds left, the full budget of time. We were trying to find a home for B. B will now fit. B cruises in and gets the assignment. At the point that B is finished, that's when, let's see, no, wait a minute. B is 20 seconds long. I better be careful. That means 20 minus 20. There's 20 seconds left here. And there's a couple things that could be done. You could do C or D. They might get the assignment. Let's check. C is 10 seconds long. D is 20 seconds long. They would both fit, which means that this is where the rule kicks in. I've got to pick one of them for the assignment. What did it say? Bold letters, choose the longest processing time first. Here we have a choice. Longest processing time is D. D gets the assignment. D gets the assignment. D was 20 seconds long, which actually finishes that station out nicely. And it's time for a new workstation. New workstation, fresh budget of time. Now, I should mark D off. I'm at the third workstation. I'm looking for who's eligible. Well, we're still trying to find a home for C. Here. I'm still trying to find a home for C. Now, who else might be eligible? Because I finished D. But I do not want to add F to the list because F doesn't become eligible until E is done, and we're not even there yet. Oh wait, that means that this is pretty easy. C just cruises in and gets the assignment. It's only 10 seconds long, right? So we have 30 seconds left. Let me mark it off. At the point that it's finished, E becomes eligible. Okay. E is eligible. It's only 10 seconds long. It'll easily fit, so it automatically gets the assignment. It's the only choice. Here at this second workstation, or third workstation, excuse me, we are now down to 20 seconds. Oh, and F finally becomes eligible because D is done and E is done. F is eligible, and I remember from that illustration, though, that F is 24 seconds long. We do have 20 seconds left, but that's not going to get it. It won't fit. Nobody will fit. That means we're done with the third workstation. We're done with the third workstation, so we open a fresh station. Station 4 now, full 40 seconds. Full 40 seconds, we were looking for a home for F. Now it's a no-brainer. It cruises right in. Now, it's 24 seconds long, so 40 minus 24, correct me if I'm wrong, is 16. Is anybody eligible? Well, yeah, actually, we only have one other task to find a home for, and that's G. But G's a full 40 seconds long. G's not going to share a workstation with anybody. It's going to hog the entire cycle time, which means that we have no choice but to close the fourth workstation's design and open a fifth one, of which G gets all to itself. Now, we have designed this assembly line. You have to remember that this is the design right here, the assignments. Now, having done all that work, what was the actual questions that were asked? Given you followed their instructions, we did. What is the efficiency of the line that you designed? The efficiency of that line. Okay, efficiency in this context is the sum of the task times divided by the number of lines in your design times the cycle time. So we just need to fill in these numbers to answer this question. Now wait a minute, the sum of the task times, that's, we could have done earlier if we wanted to, that's just the sum of all these numbers. I get 160. Oh, which it has an interpretation all by itself, right? If you were working all by yourself assembling one of these things, it takes you 160 seconds because you got to do all the tasks. Okay, that's the numerator. Now, the denominator, the number of workstations in our design. Well, that's 5, right? 1, 2, 3, 4, 5. Yeah, it's 5. Times the cycle time is 40. That's where we get 80%. Now, this question, what would be the second task performed at the second workstation in your assembly design? This is how we test your ability to design an assembly line, by asking you questions about a finished design. It's like spot checking. Okay, second task, second workstation. You just need to locate this. Second workstation, Here's the assignment, second task. There it is, it's D. Ah, there, answered. Okay, now, that was designing a product layout, right? An assembly line. The next question, actually the next two questions, the next two questions are about designing a process layout. Let's look at this. Palm Coast Hospital is designing a new building and has determined closeness ratings between the 8 departments that must be located on the ground floor of the structure. You can tell this is about process design, process layout, because that's closeness ratings is a technique for designing process layouts. Anyway, I digress. Here is a Muther diagram, right? That kind of strange house-shaped table that's so handy for organizing readings on pairs of things. Okay, anyway, yeah. What does that have to do? Just answer these two questions. Oh, okay. It's not actually asking us, it doesn't look like, to do any designing. It's just asking us about this information that's provided. Which of the following departments would Palm Coast Hospital consider most preferable neighbor to the administrative office? Okay, so I need to locate, well, duh, it's right there, the administrative office in this diagram. And it's saying, which of these 5 would it consider the most preferable neighbor? So the next thing I need to do is locate the ratings associated with its neighbors. That would be the row that's adjacent this way, you know, go out, go up, and the short row that's adjacent this way. Okay, so here's all the various ratings associated with all of the various neighbors. Now, you can see that there's a very short row below. What does, for instance, that particular X represent? That's the closeness rating between the administrative office and the food court, of which, right, now to answer this question, we have to remember, what does those letter ratings mean? They are the vowels of the alphabet, right? A, E, I, O, U, and then an X at the bottom. X is undesirable. Do not make these two things neighbors. Okay, the administrative office does not want to be next to the food court. All right, now go back up the scale. The A, right, represents the highest degree of importance to something be a neighbor. And then we have to remember, as you go through the vowels, it is lessening degrees of importance, of which I is indifference, and of which U, unimportant, represents indifference. U. Okay, A, E, I, O, U. Right, now, we still haven't answered the question. Well, what we need to do is figure out what ratings were given in each of these cases. Okay, the laboratory. The laboratory is right here. That means that this is the closeness rating between the administrative office and the laboratory, and that's a U. Okay, the gift store, administrative office and the gift store, is another X. They don't want to be neighbors. The food court, we were just remarking, that's an X. The pharmacy, administrative office and pharmacy, that's another U for unimportant. And the main elevators is an I. Now, you might be recalling from our discussion of closeness ratings and going, wait a minute, we checked out all of 5 of those, and none of them are A's, right? A was, you know, the absolutely necessary, if possible, highest degree of importance. And it says most preferable neighbor. Yeah, it says most preferable neighbor. It's not asking who's got an A rating, it's asking who's got the highest rating, of which that would be I. I is just like merely important, but that's the highest of the group that we see here. Okay, now next question. Which of the following statements is apparently true based on this information? So we have to test these based on that table. Palm Coast considers it absolutely necessary, now that would be an A, that admitting is located next to the main elevators. Ooh, that's easy. That's false because we were just talking about that. That's why it's easy. Oh, excuse me, no, administrative office. We were just talking about administrative office. We have to locate the, oh man, I have to eat my words. Don't confuse admitting with the administrative office. This one's true. Yeah. Right, admitting. Admitting and the main elevators go this way, go that way. That's what's at the junction. That's definitely is an A. Sorry about that. That one's true. Palm Coast considers it absolutely necessary, again that's another A, now let me check more carefully who we're talking about, that the gift store is located next to the emergency room. Alright, so emergency room is here and gift store is here, so go out that way, go out this way. Who is at their junction? That's an X. No, the exact opposite, that's the one that's false. They do not want the gift store next to the emergency room. Palm Coast considers it more important that the food court is located near the gift store than the food court is located near the pharmacy. Oh, all right, now to answer this question, and I kind of marked up my diagram a bit, I've got to be careful. I have to locate two different ratings and then compare them to each other. The food court and the gift store. Food court and gift store is right here. Okay, that's an E. So I can actually note that. Food court and gift store is a rating of E. Food court and pharmacy. Food court, it's going to be somewhere along this row. Pharmacy, right, where do they intersect, is a U. Food court and pharmacy. Yes, that's a U. Now, what was the statement? They consider it more important that the food court is located near the gift store, E, than the food court is located near the pharmacy, U. That's true, because E comes before U in the alphabet. That is a higher degree of importance. Okay, so that one tested true. So we have 1 and 3. So here we go for partial credit.